Welcome everyone to the second joint ELI user call webinar. My name is Alexandra Schmidli. I coordinate communication for ELI Eric. I'm sitting here with a number of my colleagues, and other colleagues logging in. I will briefly introduce the webinar, the program, and then I will hand over to our speakers. So just a few quick housekeeping rules. The meeting is recorded. We will post this on our user portal as soon as possible for others to join, also from other time zones that can't join us right now. If you would update your name and affiliation in your profile name, please do that so we can see who is asking questions at a later point. Only speakers and panelists have speaking permissions and video permissions. So if you have any questions or technical issues, please post them in the chat. We will have a question session later on. And so please post all of these into the Q&A below. We will get to them as quickly as possible. Again, if you have technical issues, you can direct those at the host in the chat. And then I would briefly go through the program. So we'll start with a brief introduction by Andrew Harrison. We'll go over to ELI Beamlines with Daniele Margarone. ELI ALPS is represented by Dimitris Charalambidis in online here, and then Zita Váradi will run us through the application process and introduce the user office, and then Sophie Chen from ELI MP will present the offer from the NP side, and then we'll have a joint Q&A and discussion session. So with that, I would like to just hand over to Andrew.
Thanks very much, Alex. So welcome everybody. I'm going to give you an overview of an introduction to ELI itself, because some of you may not even be familiar with ELI, before we go into more detailed presentation of what we're offering as facilities and also how you apply for Beam time. So ELI itself began really with the invention of the technique that allows us to greatly increase the intensity, peak intensity of laser pulses. So Donna Strickland and Gerard Moreau developed the technique of chirp pulse amplification, whereby the laser pulse was stretched in energy or wavelength, amplified, and then recompressed, allowing one to increase peak intensities by orders of magnitude. Now, that kind of technique, that technological step forward, might well have simply remained in individual research labs and be accessible by experts. The concept of ELI was to take that technological leap and make it much more widely available. And that's done by developing 3 laboratories, and we can move to the next slide, please, Alex, across Europe, which offer different variants of that technological leap forward at 3 different centers. So at ELI Beamlines near Prague in Dolní Břežany, the emphasis is on offering the highest peak intensity, but also with a reasonable rep rate. So you can also deliver high average power beams and therefore drive secondary sources of particles and radiation. Complementing that, there's the attosecond Laser Science Center, ALPS, at Szeged in Hungary, where the focus is on ultra-short pulses, looking at extremely fast processes, but also still in combination with high intensity. And then thirdly, at Margarone in Bucharest, the nuclear physics facility that provides petawatt-class lasers with ultra-intense gamma beams, tunable up to 19 megavolt rather, not millivolts, to produce and explore nuclear states, and also to generate secondary beams, in particular neutron beams. And what those 3 facilities have to offer will be presented in a little bit more detail in a moment. Now, 2 of those facilities, Beamlines and ALPS, have also combined in essentially the same legal entity, a legal entity called an ERIC, and that confers on them certain advantages financially and so forth. But importantly, also it provides a common framework within which they can develop and share all sorts of processes and so forth, and together develop the facility in a coherent fashion, so that in future, when users come, their experience will be essentially the same across the facilities. And the ERIC itself has a number of members. It has the founder members and the funders, Czech Republic and Hungary. Around the table, we also have Italy and Lithuania, who are members, and then there's observers, Germany and Bulgaria. And collectively, these countries support provide funding to support it, and then complementing that, the third facility, ELI-MP at Margarone, is also working closely together on the technological side to ensure that collectively we provide a complementary suite of technical capability. Move to the next slide. So the concept essentially is to allow these very high-end, provide these very high-end laser facilities to a much wider user community. Our users may be already laser experts, but increasingly what we would hope is that a wider range of scientists learn how to exploit these facilities for their own end. And there are broadly many types of applications that the combination of high intensity and high average rep rate may support a wide variety of science. So the facilities, depending on which one we focus on, produce high intensity secondary beams or electrons and X-rays. They can be used as very compact particle accelerators to provide a variety of ions up to 250 megavolts in energy. They can be used directly in material science and biology to probe the structure and the dynamics of materials and biological systems. And at these very high peak intensities and powers, they can also generate plasmas, which are themselves a focus of a lot of studies, and are also related. Many of you will be aware of the recent advances in laser-induced fusion. So there's a particular interest at the moment in exploring the potential for these facilities to provide an alternative to the magnetic confinement technology that's being also developed to explore the possibility of making nuclear fusion a viable energy source. And then finally, at these very high intensities, these facilities are approaching the intensity limits at which you actually start to create out of the vacuum matter and antimatter, and look at some of the very fundamental properties of physics at extremely high intensities. And then complementing all of that, of course, in building and developing these facilities, we also have to develop the laser systems and the secondary sources as well. So in addition to the science that we support, there's an awful lot of activity in the development of lasers and the associated technology. So ELI itself has been operational at least in the commissioning state for a number of years. Over the last few years, it's ramped up hugely in strength. We have hundreds of employees, almost 600, just in the ERIC, ALPS and Beamlines, drawing on 30 plus nationalities, so a highly international organization. We have collaboration, both in technological development and also in scientific programs across most European countries. The top right map gives you a flavor of the reach in terms of international engagement, and of course beyond Europe as well. Very strong engagement, for example, with Japan and the US, and complementing that to a very healthy increase in publications flowing from ERIC. But of course, the key engagement that we're keen on encouraging, and the one that's the focus of this webinar, is with the wider user community. So it's absolutely essential that we provide a service, often to people who are not experts, people who have not yet really started to explore how to exploit these facilities. And the key instrument that we use is open excellence-based access. in the years to come, we will also be offering more targeted access in mission-based areas, so areas such as areas that essentially map onto societal challenges, such as developing new technology for greener energy or for new therapies and in medical research. And over the next year or two, we will be launching coherent programs also to encourage and support activities specifically in these areas. And of course, we're open to industry. Our facilities are very much open to companies who wish to buy into the facility and pay for proprietary access. And interest in that is starting to rise. But here and now, we're talking about open, excellence-based user access. The first call was launched in the summer of last year. We, even at an early stage, we got a very healthy level of interest, and those experiments are now being rolled out and supported from just before Christmas. In the first call, we only offered 10 Beamlines and secondary sources, and that saw a very strong step up in the second call, which was made a month or two ago. So we're now offering, Alex, I think the latest count is 34 different instruments, be they the primary lasers, some of which can actually be used in their own right directly, but many of which drive secondary sources, which themselves have end stations. And what Daniele and Dimitris and Sophie are going to present now in a little bit more detail is what is offered in terms of equipment at those three facilities. I should just end before I hand over saying that these are all accessed through a single point through the ERIC. We're coordinating this call in collaboration with Eli NP. Access is free. It's based on peer review evaluation of scientific excellence. So your proposals will be reviewed by a panel of external experts. And if you have any queries on the instrumentation beyond this call, the key thing to do, but Zita will come back to this, is to contact the individual experts within the facilities who are associated with each instrument, and you'll be able to find out who to talk to for each particular instrument at the website whose URL is given there. But at this point, I'm going to hand over to Daniele, who's going to tell you about what's on offer at Beamlines.
Thank you very much, Andrew. Well, I will be focusing, of course, on the Eli Beamlines facility down in Brzezany, near Prague, in the Czech Republic. And I want to remind you, if you have questions, please use the chat. I'll try to answer during the remaining time after my talk, but especially if you have technical questions, please look up at the web page, and each of the instruments we have online. For each of the instruments, we have a contact person who will be very happy to answer your questions. So let me start with the mission profile of Eli Beamlines. We are operating cutting-edge, high-power femtosecond lasers, actually 4 systems. Each of these systems is unique in its own category, based on a combination of high energy and high repetition rate capability. We will discuss a little bit about that in a second. Those lasers are used to explore interaction of laser matter interaction, or if you want, laser plasma interaction at ultra-high laser intensities. But here at Eli Beamlines, we are using these lasers mainly to offer secondary sources, particles and high-energy photons, X-rays, gamma rays, to users with unique capabilities. I will talk about that as well. Well, in a certain sense, we have 2 groups of users. The first group, user performing fundamental science, fundamental research in plasma physics, high field physics, nuclear fusion, and laboratory astrophysics. And then broad and heterogeneous group of users who want to explore the use of our secondary sources for applications in material science, biology, chemistry, medicine, and others, all of them with a strong multidisciplinary impact. Okay, this is a layout of the Eli Beamline facility. Our 4 laser sources are sitting on the ground floor. You can see here, we call it L1, which is L2, L3, L4. L1 is a multi-terawatt kilohertz class laser, already available for user within Eli called one, and now we are talking about the second call. Then the L2 laser is a 100 terawatt class and 100 hertz class laser, which is still under development. Probably will be available in 2 or 3 calls, so next year. And then the L3 pulse laser, this is considered the workhorse of the Eli beamline facilities. It's a petawatt class and 10 hertz class laser, which drives several of our secondary sources, high energy secondary sources. And then the L4 10 petawatt class kilojoule laser. You will see that we are not offering the 10 petawatt capability yet, but we want to offer this laser in its uncompressed fashion, nanosecond beam. Each of these lasers can be distributed to several experimental stations in the underground floor here. And in fact, we use the L1 laser or L1 E1 chain. I'll be talking shortly about the E1 experimental hall for user experiments in the field of materials science and biomolecular applications. And this chain is online since 2019 and part of the Eli Gold 1. So our ERIC users are performing experiment at the very moment here, and we will offer the same capability for the Call 2. And then the L4 uncompressed version has been commissioned and is available within Call 2 in the plasma physics area down here. We'll talk about that. The L3 laser has been commissioned both in the plasma physics area and in the E4 area, where we perform ion acceleration, but also can be used as a platform for ultra-relativistic laser matter interaction with solid target, and we are going to offer these within Call 2. And finally, just to give you an idea about what you can expect in the upcoming calls, we are currently commissioning the electron wake field accelerator in the E5 hall, and we plan to have it online in August for Call 3. And next year we will have probably online the high energy X-ray sources, the Betatron radiation in the E2 hall, and at some point also the undulate or water window radiation, the E5 hall. Here I gather a few pictures to show that Eli Beamlines is not only layouts and animations, but there is a real experimental action and user action in our hall. So you can see here on the left the L1 E1 chain, where we deliver a photon from the mid IR to the hard X-rays at 1 kilohertz to drive secondary sources, and then perform pump probe experiments with resolution or delay from the femtosecond to millisecond to probe dynamics in a very broad range, temporal range. The L3 E4 chain, where we provide or we perform ultra high intensity laser matter interaction, ultra relativistic intensity beyond 10 to 21 watt per centimeter squared. And of course, and also we provide ion beams, particularly proton beams with high energy. We'll talk about that, potentially possibility to use these beams for tertiary sources. And then the L4 E3 chain, where, as I said before, at the moment we provide a kilojoule class laser, nanosecond, high rep rate, 1 shot a minute or so, with pulse shaping capability at the second harmonics. And this is of interest in general, for the high energy density physics community, and more in particular, inertial confinement fusion, shock physics, and others. This is a table summarizing the performances of the 3 lasers that will be provided or that will be online for the call, are online already and will be offered within Call 2. L1 Allegra laser is an OPCPA system based on terbium YAG, thin disk, and fully diode pumped. Currently, the system can deliver up to 55 millijoule. We don't deliver all the time in all the target areas of beamlines this energy. I will talk about that, but 55 millijoule has already been demonstrated on target. Very short pulse, 15 femtosecond, few terawatt on target and operating at kilohertz, but of course it can be used at reduced rep rate 100 and 200 hertz. This is an OPCPA system, so the contrast is intrinsic contrast is very nanosecond, intensity contrast is very high, 10 to the minus 10. The L3 HAPLS laser is a CPA system based on titanium sapphire technology, also in this case fully direct pumps. The laser is a petawatt class laser, but we did not ramp it up to 30 joules yet. So we provide at the moment about half a petawatt, 13 joules in 27 femtoseconds. And this can be run up to 3.3 hertz. Of course, with the solid target, it's a little bit more different. You will see that we have demonstrated 0.5 hertz operation on solids. The contrast, we have been working on the nanosecond contrast, intensity contrast, and currently we can provide quite clean pulses with a contrast of 10 to the minus 11. The L4 atom laser, as I said before, this is a 10 petawatt laser, will be ramped up early next year, and the first commissioning for the 10 petawatt is planned for early 2024. But now we want to offer the uncompressed beam to the high energy density physics community, and in fact we can deliver half a kilojoules with the possibility to tune the pulse duration from 2 to 10 nanoseconds and one shot every 3 minutes. Even if we can run at 1 shot per minute, in fact we have demonstrated the reliability of the laser at 1 shot per 3 minutes, and this is what we want to offer. Then a few more insights about the E1 experimental hall. As I said before, this is a kilohertz area dedicated to application in bio and material science. We have a number of secondary sources and also user stations or end stations. The first one is the high harmonic generation from gases that can provide XUV source at kilohertz in the range between 5 and 120 nanometers. This source or those pulses can be isolated using a monochromator, and in fact are delivered to users into a station called, we call it MAC, multi-purpose station for hemoscience, atomic, molecular, and optical science, and also a coherent diffractive imaging. Very often our users are benefiting from the pump probe setup that we offer within this chain. And in fact, we can synchronize with femtosecond precision the X-ray source and the optical laser as a pump and probe setup. Then the plasma X-ray source is the hard X-ray beam, available again for one of our end stations, the T-Rex station, where our user perform experiment in the field of X-ray diffraction and X-ray spectroscopy. Here, either the Bremsstrahlung radiation from 3 to 30 kV can be used, or the 8 kV K-alpha line coming from the fact that we are using the copper tape drive at the moment. And then on the upper right corner here, we have an area for ultra-fast optical spectroscopy, and two kind of experiments, user experiments, are being performed at the moment: time resolved spectroscopy ellipsometry and transient current technique. You can see here on the right that this area, in fact, can be driven by not only by the L1 laser, and in fact, in this case, we deliver about 25 millijoules reliably, 8 hours a day at kilohertz. But this area, in fact, or the sources that I have just described, can be driven also by support lasers that are commercial solution in parallel. So in fact, here normally you can have 2 or even 3 user groups working in parallel. That is the only case. Plus, we also offer a satellite laboratory for ultra-fast optical spectroscopy. It is in another building. We call it the BioLab. And here, the optical lasers are used for transient optical absorption and femtosecond simulated Raman scattering. Then I'm not going through each of the line that you're going to see here, just to say that our user community for the E1 hall is quite diverse and in fact performing experiment in the field of science with coherent XUV radiation, including XUV source development, which is part of our user community. The same for the hard X-ray science. We also have plasma X-ray source development. And then the ultra-fast optical spectroscopy I just described is performed in the E1 hall and in the biolab. And on the top of that, we also offer support labs for sample preparation, including samples that requires preparation in biosafety level 2 laboratory, and also characterization, for instance, using electron microscopy. Well, this is actually, I did not mention this yet. It's a pilot project that we perform directly in the L1 laser hall, and we call it Alpha Station. It's a kilohertz laser plasma accelerator. And we want to offer this within Call2 for the first time with three, if you want, in 3 different fashions. First one as a platform for kilohertz experiments at relativistic intensity. In fact, in this case, the energy available on target from the L1 laser is 55 millijoules, and we have demonstrated intensity above, well above 5 × 10⁻¹⁰ watts per centimeter squared. As this is one use. Then the second use that has shown electron beams with superior characteristics. So for electron beam acceleration at kilohertz, energies up to 30 MeV, quasi-monoenergetic beam, and continuous beam. Actually, this is a beam. Finally, here we can speak about an accelerator, a laser accelerator in terms of current. So this is the average current up to 300 picoampere. And the third way, or third type of use of this station would be sample irradiation with the electron beam that we can provide to the users. In-air irradiation. Then also in case of the laser plasma ion accelerator, what we call LMIA beamline, we want to offer within ELI Call2 the beamline in 2 ways as an experimental platform for ultra-relativistic laser matter interaction. So we demonstrated with about 10 joules on target intensity up to 3 × 10⁻21 watts per centimeter squared. And these have been demonstrated at a repetition rate of about 0.5 hertz on solid targets. You can see here in the bottom plot that we have been working last year on the intensity contrast of the laser, and in fact, what we offered when we published the Call2 was something like 25 MeV proton energy, cutoff energy, and recently we performed our advanced commissioning and we demonstrated much higher cutoff energy up to 40 MeV with increased intensity contrast. The second part of the beamline that you see here on the right is, we call it LEMED, is the ion beam transport, and dosimetry and sample irradiation will not be offered within Call2. You can see the expected performance here, and this is just something that I want to anticipate for the next call. We are going to perform our commissioning at the moment. Last but not least, the P3 plasma physics platform in the E3 hall. As I said, within Call2, we want to explore the interaction of the uncompressed kilojoule beam. You can see here in the picture, or in this nice animation, that actually this platform can accommodate different laser beams, the L3 beam, the L4 beam, in different modalities. But at the moment, only one beam, I want to stress this, will be available here, the L4 uncompressed. And the peculiarity of this beam is to have high energy kilojoule, high repetition rate, one shot every 3 minutes, still considered very high repetition rate. There is no other kilojoule nanosecond laser worldwide with this rep rate available for user at the moment. Plus the combination of running the laser either with a narrow band or with a broadband features. That is important for laser plasma instabilities, which is in turn important for the inertial confinement fusion. Also, this area here will be available with a number of diagnostics, which is provided by our team, laser plasma instability, shock physics diagnostics, but also hard X-rays, and a number of target solution or target delivery solutions, solid, gas, foam, both on tapes and on the rastering systems. That's all from my side.
Okay, thank you, Daniele. And now we move on to Dimitris, who will introduce us to ALPS and give an overview of the offer that's in that second user call. Go ahead,
Okay,
Dimitris.
thanks, Alexandra. Good morning, good day, good evening from where you are now. I will present the ALPS facility, and I will focus mainly on the technologies that are offered in this second ERIC call. I will start with the mission of ALPS. The main mission of ALPS is to provide to users state-of-the-art equipment for performing studies of ultra-fast structural dynamics in all states of matter, in liquid phase, gas phase, condensed matter, and plasma. Next, please. I will start with the structure of ALPS, which is what is the philosophy of ALPS. ALPS consists of primary sources, meaning lasers, that are driving secondary sources, particle and photon sources, and both the lasers and the products of the secondary sources can be used for experiments in experimental setups that are offered by the facility or are brought over to the facility from the users. Now, the lasers, we have several laser systems. I will not go through all the parameters. You can find them on the website of the call. I don't have the time to go into many technical details, but I want to stress that we have lasers that have repetition rates that are ranging from few hertz to 100 kilohertz, and pulse peak powers that are ranging for 0.1 terawatt to petawatt. And what I want to stress about the lasers is that for the energy level of the pulse energy level of each system, the repetition rate of the system is the highest existing at the moment. The secondary sources are mainly harmonic generation sources. Harmonics are produced either in gas phase or on surfaces. And we also have other photon sources like terahertz radiation sources and electron acceleration secondary sources. On the end stations that we're providing, I will come later during the presentation. Next, please. This is an overview of the facility. You see, this is one of the buildings that you have seen in the first transparency. It's a square area that is decoupled vibrationally from the rest of the world, and it hosts the lasers and the secondary sources. You see four main experimental areas on the left and upper sides of the side of the transparency. The right middle one is the area where the lasers are located, and the other three holes are experimental holes with different radiation shielding, depending on which laser is used for driving the experiments. The facility is based on activities that are presented here with different colors. You see different colors. Each color is representing one activity, and the activities are including lasers, secondary sources driven by the lasers, and end stations. The name of each activity is coming from the laser that is on the origin of this activity. Next, please. In the first call, we have offered very few equipment that is summarized on this transparency. And in the second call, next, please. we offer more technologies. You see here that we offer technologies from the activities of the high repetition rate laser. This is in blue, or of the silos laser, which is in green. Then we offer also terahertz radiation capabilities, mid-IR laser and end stations, as well as 3 labs: the nanofabrication lab, the radio biological lab, and also the chemical reaction control unit. Next, please. Now, in all these next transparencies, I will present the different activities, meaning laser plus secondary source plus end stations. And the layout will be like in this transparency. In the upper panel, you see the lasers and what they are driving. And then there is a table. And in this table, we summarize what is offered during this call. I will not present things that are under development. I will focus only on what is offered in this call. The first activity is the mid-IR activity. The mid-IR laser is emitting at 3.2 nanometers, is a 100 kilohertz system, and the pulse energy is 150 microjoules. And this is, it can be pulse compressed to a shorter pulse, and the laser can be used with a VMI electron spectrometer, which is a development of the Max Born Institute in Berlin. You see it there, exactly. Or with a reaction microscope or Coltrim's device, which is a commercial product from the Rontec company. With this device, you can do ion electron or electron ion coincidence experiments, utilizing the high repetition rate of the laser. Next, please. The next activity is the high repetition rate laser activity. At the moment, there will be 2 lasers. At the moment, only the one is offered. It emits 1 microjoule near IR pulses with a repetition rate of 100 kilohertz, and it is pumping or driving 2 harmonic generation sources, gas phase harmonic generation sources. And these sources are coupled with several end stations, like a reaction microscope end station, VMI. It's the same like the one of the MIR activity. Those are portable end stations and can be moved to the HR activity, or a transient absorption spectroscopy unit, and also a very advanced nano ESCA system that is an end station for surface science. Which can be also used using the femtosecond oscillator of a femtosecond oscillator laser system. Now the HR system can be operated in 2 modes: in a long pulse, 30 femtosecond, or a short pulse, 7 femtosecond pulse duration. And the leakage of the laser beam can be used in some of the experimental setups, like the transient absorption spectroscopy. I will show you now the two gas phase harmonic generation sources, attosecond sources. Next, please. The first one is shown here is the development of the CNR, the Politecnico di Milano, and the CNR IFN in Italy. It produces attosecond pulse trains with a pulse duration of 166 attoseconds. The pulse energy at the generation is about 250 picojoules, and 50 picojoules of which are reaching the target of the experiment. And of course, this source is operating at 100 kilohertz because the driving laser is 100 kilohertz. The system is appropriate for XUV IR pump probe experiments, and it's a rather versatile system. The photon flux that is offering is the highest for this repetition rate at the moment. The second beamline is very similar to the first one. The developer is the same one. And the difference is that it includes also a time compensated compensating XUV monochromator, with which one can select a certain spectral range from the entire the harmonic generation spectrum. And the monochromator is such that it compresses the pulses, the XUV pulses, to the shortest duration that is supported by the bandwidth of this spectral range. And then this beamline is now dedicated for condensed matter of surface science studies, and which is done with a nano-ESCA system. And later we will also have a liquid jet facility in this room as well. Now, the nano-ESCA system is a commercial product by the company Sienda Omicron. Is in a very advanced end station. It is a photoemission electron microscope with energy resolution, either using a time-of-flight energy analyzer or a double hemispherical energy analyzer. It can operate in, record images in real space or in K-space, in momentum space. And in this ways, you can map the entire dispersion curve of solid materials, and is also equipped with a unique spin filter, imaging spin filter, based on iridium crystal, gold-coated iridium crystal. The instrument can be operated either with a CW XUV lamp that is included in the system, or with the oscillator that is now offered, laser oscillator that's offered in this call. And later on, it will be operated also with the attosecond beamline and the laser itself for XUV IR time resolved dynamics on surfaces. I should add also that the instrument consists of the nano-ESCA, but also with a preparation chamber where we have a large number of diagnostics for the sample preparation. Next, please. The next activity is the SILOS activity. The SILOS system is 1 kilohertz. It consists of two systems, the SILOS alignment system and the SILOS itself. The SILOS itself is a 1 kilohertz system, is on commissioning now and is not offered in this call. The SILOS alignment laser is a 10 hertz system. Both systems are emitting pulses with energy of the order of 30 to 40 millijoules. The pulse duration is either around 12 femtoseconds or compressed with lower pulse energy at around 5 femtoseconds. And this, the alignment laser and the silos are driving two gas harmonic generation sources, and are also in this activity is also included a device for chemical reaction control and dynamics studies. Next, please. So the two harmonic generation sources that are driven by the silos laser, in this called by the silos alignment laser, is the compact laser. The so-called compact is not that compact is something like 20 meters long beam line. It produces harmonics in gas jets or gas cells, and I'm showing you here some spectra that were recorded. This is in argon. In xenon, we reach the level of 1 microjoule per attosecond pulse train. And in neon, we were able to produce photon energies up to 150 eV. Next. Now, the XUV energy level that we reached is high enough to induce nonlinear XUV processes. There was an experimental campaign in collaboration with Fourth and LA ALPS that has demonstrated 2-photon direct double ionization of neon using solely the XUV radiation of this beam line, which verifies that this beam line allows for XUV pump, XUV probe experiments. And to this beam line, of course, the VMI electron spectrometer or the reaction microscope end station can be coupled, but the beam line itself has other capabilities like time of flight spectrometers for electrons, ions, or ion microscope spectrometers. Next. Okay, and the beam line includes also a facility of polarization gating, which when operated, the discrete spectrum of the harmonics becomes continuous, meaning we don't have any more than attosecond pulse, but an isolated attosecond pulse. Next. This is the second attosecond beam line that is driven by the silos lasers. Is the so-called long gas harmonic generation beam line. It's a development of Lund University. It's a very long device. It extends over 3 laboratories. Allows for focusing with focal lengths of several tens of meters, and the target is a series of gas cells, 16 gas cells. This is shown in the upper right panel. Yeah, exactly there. It's the length of all these cells is 6 meters, so the focal area is very long. And each cell the pressure of the gas in each cell can be controlled separately, and this allows for optical optimal phase matching in the harmonic generation process. Up to now, this beamline has been operated with shorter focal lengths, and some spectra that have been recorded are shown in this transparency. Another capability of this beamline is an interferometer, a split and delay unit shown, exactly there, where several colors like the laser, the second harmonic, third harmonic, and the harmonics generated by the beamline can be split. One or several of those can be delayed and then recombined again in order to do pump probe experiments with different colors in the final end station, which again can be one of the end stations I was talking in the previous transparencies. Next, please. The next activity is the terahertz activity. There are two terahertz laboratories, the nonlinear terahertz spectroscopy facility, which is offered during this call, and the high energy terahertz facility, which is in commissioning and can be also offered during this call. It's not operational yet, but when the experiments of the second call will start, will be operational in the facility. You see the parameters of both devices. Units, the nonlinear terahertz spectroscopy facility is a kilohertz system and emits pulses with energy of the order of 10 microjoules, while the high energy facility is, at least during the site acceptance test, was emitting pulses with an energy of 1 millijoule, and it operates at 50 hertz. It's single cycle pulse. The spectral range is 0.1 to 1 terahertz with a peak at 0.25 terahertz, and can be synchronized with a driving laser at 800 nanometers. Next, please. This is a transparency showing the transition, the transient absorption spectrometer that is operated with the HR laser system, the high repetition laser system. The probe is either through a white light that is produced in a sapphire crystal, or with a UV light, which is the second harmonic produced in a BBO crystal. And that's all about this. Next, please. This is my last transparency, which is the nanoscience activities. It has two facilities. The first one is a scanning near-field optical microscope, which can be also used for electron beam lithography, and has also a focused ion beam facility for producing nano samples. You see parameters like wavelengths here and powers, but I think what is important to stress here is that the lateral scanning resolution is 5 angstrom. The vertical scanning resolution is 2 angstroms, and it can accommodate samples of about 1 centimeter to 1 centimeter and 1 millimeter thick. And you see also the scanning ranges. And the second device is an ellipsometric setup, which can be operated in a time resolved mode, so it's appropriate for ultra fast ellipsometric studies. That's all I wanted to convey to you. Thanks.
Thank you, Dimitris. And now we move on to the user portal and the application process, and I will hand over to Zita here. I hope one thing I wanted to say briefly is I did see some hands being raised by the participants. Again, I would encourage everyone to just post their questions in the chat, and then we can address them afterwards. I see Daniele has already responded to some of them, but all right. Without any further ado, Zita.
I don't know whether I can be seen or not, so my camera on my computer is not working. I'm sorry for this.
So we're switching around a little bit. So there we go. So Zita is speaking from Daniele's computer.
Okay. Thank you. My duty is today to walk you through the user portal and the application process of Eli Eric. The user portal is for all three facilities and the proposal submission as well. I will walk you through in practice, and the review process is related to the Eli Eric proposals. So you see below our timeline, we are at the yellow dot today at the webinar. The Eli Eric submission deadline is the 25th of April, so you still have a little bit of time for preparation. We schedule the beam time to be allocated, so the assessment process finished by the 16th of June, and we hope that we can notify all users about their successful proposal by the 30th of June. This will give us enough time to prepare and schedule the experiments so that these can be carried out between August and January, because this second call should be performed within this time period. Until the users are notified about their successful proposals, Eli Eric user office is handling the proposal or managing the proposals. And afterwards, these will be handed over to the facilities. In case of Eli NP, after the submission deadline, which is a month earlier than ours, the proposals will be sent to the local user office to Eli NP, and this will be presented by Sophie in the next talk. Can you go to the next slide, please? So I'm almost sure that you have all visited already our user portal. We have here information for you about the user calls, about the offer what we offer you to use for this second call. We have a user guide how the portal and the proposal management portal should be used. A very important point is the terms and conditions, because by submission you should accept all the terms and conditions, GDPR and the GDPR notice. And there is a very important point, my proposals. I would like to highlight the possibility of browsing around all the equipments we have. There is a possibility of filtering according to different aspects of all our equipment, and you can choose here your equipment and click on it, and then can you please go next slide? Thank you. So the basic information you will find on each equipment on site. And you will get basic information and even more about the available setup, the geometries, the target system, and so on. What I would like to emphasize is that at the top of each page, you find the relevant contact persons, the scientists who are experts in the given field. So if you have any questions about the given equipment, you should contact them directly. And again, I would like to emphasize here that the local scientists will not see your proposals before it is in a submitted phase. I will come back to this later on. Can you go to the next, please? So first you have to register and create an account on our ELIARIC user portal, and then we have an online form where principal investigator is submitting a proposal describing the scientific and technical content. And as I mentioned already, the terms and conditions and the GDPR notice is a must to be accepted. I would advise you, before you start, go to the user guide and you can go through again the steps. I will just highlight you now. There is also strong advice from us that you save or bookmark the address on your computer, because you can enter and re-enter your submitted proposal, and you can even communicate within the portal with the user office. Next, please. So how you create an account? Of course, you go for apply for Beamtime. You can, thank you. And then you have to sign up to the user proposal management system. I would advise you to use a valid and used email address, because an email address which you use frequently, because you will receive automated and even not automated messages from the user office and from the portal, and this will be also the possibility to contact us about your proposal. You will get registration confirmation in an email. If you don't find any email soon in your email box, then please check your spam folder, or in the worst case, please contact ELIARIC user office. Once you are registered in the ELIARIC user proposal management system, then you will be able to start filling the online form. You should click on the green proposal button or icon if it is not opening for the first time. The first entry is your name, and or this is your registered part, and we ask you here to start with the proposal title, and just below that, this is the attachment field. This is a safety field. If you fail to copy paste your figures or diagrams into the given text field, please come here and attach your figures, but make sure that you reference it so that it can be understood later by the feasibility reviewers and also the scientific referees. And then please indicate your personal information. Not only the principal investigator, but the whole experimental team should be indicated in the portal. Later on, the scientific and technical content, and we have also other questions which is necessary to assess the feasibility and also the safety risks. So if you have samples or equipment to be sent over, we also would like to have some information on that before the experiment. Please check all the mandatory sections. If you are failing to filling in these sections, which are marked with a red asterisk, you will not be able to save or even to submit. Here I have to tell you that you are able to come back and edit your proposal as many times as you wish until before the submission deadline. This means that even in the best case that you finished your proposal at the best for the first time, by pushing the send button, you are doing it as a save of the proposal. So it will be in a draft mode, and you have to revisit.
Sorry.
You can go. You can go. You should revisit either access your account from your saved option, or if you go to your proposal, click please, to my proposal option, then you will be able to come back and edit your proposal. This is the form how it will look like. So if you click on the edit button and you even just change one figure, then save and submit or save button will appear on the upper side. And if you want to finalize it, you should click the blue button. But if you are not ready with your proposal, then you should click on save. Here again, if you go through the questions we are asking you, and you need some help from the equipment scientists, please contact them and come back and fill in the form. This will make easier to assess the feasibility and even make sure that your experiment can be feasible. Next slide, please. Thank you. So I explained to you how to submit. You visit again my proposals, select the submit button, and then after the submission, your proposals are for you only a read only. But below the whole proposal section, there is a comment section where you can ask questions if you have or further requests. So you just go to your account again, and you send us any question and save it, and you will get notifications in your email box if we are answering to these questions. Next, please. Okay, we are at the proposal review already. So once the proposals are submitted, and we will review all the proposals. We will see within the portal whether by the submission deadline some are still in draft. We will send you notifications to not to forget to submit it if you still wish to. But by the time of the deadline, we will ask you to save and submit your proposals, because only submitted proposals will go to the next step, to the feasibility and safety assessment, and to the scientific review, which is already mentioned by Andrew, that this is the scientific review is assessing the scientific merit of your proposals and gives advice to the ELI management in scores and in ranking. Next slide, please. The final approval of the proposal will be done by Eli Eric, Director General, and at Eli Eric and the Eli MP Director, based on the assessment of the peer review and the feasibility assessment. As I mentioned, the scheduling and preparations will be managed by the facilities, and you will be contacted right afterwards by the local user offices. And again, please contact Eli Eric user office or use your account in the user portal to contact us. Thank you.
Thank you, Zita. And I will move on right away to Eli NP's presentation, and that's Sophia Chen, who is joining us online. Sophia, go ahead. We can't hear you.
All right, I was on mute. Okay. So
There
good
you
morning,
go.
good afternoon. Thank you. My name is Sophie Chen. I'm the head of the users office at Eli NP. I just want to first say thank you to Eli, Eric, and their staff. It's been a pleasure working with you all on the second call for users. So I'm just going to go over briefly about the instruments that are available at Eli NP. So we have one laser feeding into several experimental halls. Right now, what's available to users is the E4 and E5 experimental halls. And so at E4, we have our 100 terawatt. Several numbers to keep in mind that are important. It's 2.7 joules, 27 femtoseconds at 10 hertz. The other experimental hall, which we call E5, houses the 1 petawatt beam. Those numbers to keep in mind is 25 joules, 24 femtoseconds at 1 hertz. So I know that there's been a lot of questions about perhaps a second beam, a long pulse beam. So those are envisioned in the future. It's not available right now, but we're keeping that in mind. Also, I should mention our 10 petawatt beam in our E1 experimental hall. It is being commissioned this year. So as soon as that is finished, we will make that available to users, hopefully in the near future. So I know all of these numbers are a bit dry, but I'd like to use the next slide to illustrate the stability and performance of our laser. So, okay, before you start reading, because there's a lot of text here, I just want to give you a little context of where this sits experimentally. So 15 years ago, when I was first doing laser plasma experiments, the laser stability was not great. It was more than 20% fluctuation in energy, which made debugging diagnostics, your target, your experimental setup, very, very difficult. So on top of that, the next shot was in 3 hours. So that really made things difficult, wasted shots, wasted time. So you contrast that with what is now available. You've heard from the other Eli facilities that repetition rate is something that is very desired in performing experiments. So here, I want to give you an idea. So say you came to our facility, to the E5 experimental hall, and you used our 1 petawatt beam. Say you want to produce proton beams using the TNSA process, so you have a solid target. What you would expect if you sent your proton beams into our Thomson problem, which is a diagnostic that would smear the proton beam in spectrum. So here on the left is what you would see. You would smear in this case, it's going from top to bottom. So your high energy on the bottom, smeared across towards the top to low energy on an image plate. So here I'm showing you proton beam traces from 33 consecutive shots at 2 joules at 1 hertz. So the proton cutoff energy, which is the high energy drop off in that proton beam, is about 7 MeV with a shot-to-shot variation of plus or minus 5%. Then to its right, I'm showing you 7 consecutive shots delivered at 20 joules at 1 hertz. Here, the cutoff energy is a bit higher, of course, with 20 joules. So 25 MeV with the variation of plus or minus 10%. So this is in stark contrast to what I've been used to starting out in my career. And this is a remarkable example of what can be delivered today at these laser facilities. So I should add that the shots were performed using a tape target system. So here it's a 13 micron thick Kapton ribbon. And the system was developed in collaboration with Eli Beamlines and STFC at the Rutherford Appleton Laboratory in the UK. So it's a quite nice instrument that will be hopefully made available to users at several facilities in the future. So next slide. Next slide, yeah. Okay, so I'd like to go over some details about this call for specific to ELI&P because it's slightly different. So I just want to emphasize that our deadline is for proposals is in 1 week. It's March 24th, and we did that to provide sufficient time for our users to prepare for experiments. The period for experiments is slightly different as well. It goes from August this year to March 2024. We have a independent review process. The process is near identical to the other two facilities. There's a technical review and then a scientific review, as well as we organize presentations from the PI that submitted proposals. So we give 15 minutes to give PIs a time to present a summary of their proposals, as well as answer questions that may have come up during the review process. So as mentioned by Zita, please contact us either through the Eli Eric portal or through our email address. Whichever way, it will find its way to us. We're more than happy to look at your experimental setup, your designs. We don't want your proposal to be rejected on a technicality. I mean, so the service is there for you to use. As well as we're open to long-term developments in diagnostics, extended capabilities of lasers. So we're open to that sort of collaboration as well. So with that, I thank you. I look forward to seeing your proposals. So thank you.
Thank you, Sophia. And that concludes the presentations. I will hand over back to Andrew briefly to close it, so to speak, and then we go into the discussion or some questions, some of which have already been answered, but we'll address briefly as well.
Thanks, Alex, and thanks everybody for that overview. But really just to end up with 2 points. One is that an awful lot of the development of ELI, including opening up to the user community and providing support for a widening range of experiments, has been through an EU-funded project called Impulse, which also supports technical and scientific collaboration and involves partners right across Europe. So that's been instrumental in helping us open this up. So many thanks for the funders for that. And also to say that another important activity, of course, is to train people to better use our facilities. So again, mindful of the fact that our user community is increasingly coming from areas that have not necessarily had expertise in lasers, and those who come from labs who have laser expertise but would like to understand better how to better use our facilities. There is the second Eli Summer School. The first was in Szeged last year. The second Eli Summer School. Sorry? The second Eli Eric Summer School. I'm sorry, I stand corrected. But it's the 8th edition. Okay. Thank you. Those whose memories last longer. Thank you. And that will be held in Dolny Brzeżany at Eli Beamlines between the 29th of August and the 1st of September. And more information is available on that in the website listed there. And then finally, really just to underline the fact that if you want further information, you can contact the user office. Zita and others will be very happy to help you about aspects of the proposal process. And for technical details, please don't hesitate to contact directly the instrument responsibles, the equipment responsibles rather, whose names are on the call website alongside whatever instrument you wish to find out more about. And without further ado, I think we're very open to further questions, and we'll do our best to answer them. So please, if you could put questions in the chat, we will then direct those to whoever is best placed.
So right. I'll jump right in and just point out some of them have already been answered by Daniele. And I just wanted to So one of the questions was whether there will be another user call. There will be another user call. We will have, maybe I can direct this.
Yeah, really just to say we are rolling out now a timetable such that there will be 2 fixed points in every year. You should then be able to anticipate that well in advance. The user portal, the various tools that we are putting in place to support applications and support review will also continue to be developed. This is very much a learning process for us. And we would anticipate that what we offer in terms of the tools for support and so forth also improve in the next and subsequent user calls as more users come on stream and we learn more about how best to support them.
That's right. And then there are some technical questions, but one that I also wanted to address briefly. There was a question about hiring and recruiting at Eli. So we're still in the process of aligning our websites, our communications channels and everything. So right now, I just wanted to point out that all of the open positions are listed on the facility websites. And we are doing our best also to list those on the Eli Eric website. We will start to align this more and more so we can also promote from Eli Eric, also promote all of the job openings at the facilities locally. So if you're interested, feel free to reach out to our user office, but of course also our HR. We are always looking for new technical staff and new talent.
Absolutely.
And I will, from one of the technical questions that hasn't been answered yet, is for Sophia, and I see she's already typing, but maybe if you want to respond to it live, Sophia, feel free to do so.
Yeah, that's fine. So the question is, how many slots will be available at ELI-NP this run? Okay, I'm not going to say I don't know, but it is still being decided on the exact number of slots. So the last period from the first users call, we had 2 experiments at E4 and 2 experiments from E5. It will be probably something similar, but if you email me in a couple weeks, I can give you an update as to the scheduling, but that's all I can say right now.
And I think that underlines quite an important point, which is, of course, across all 3 facilities, we're very much ramping up on all the instrumentations. So not only will we be bringing yet more equipment online for the next call, but the current range of equipment is also being improved and developed pretty much on a continuous basis, whether it's in terms of the peak performance or whether it's the reliability and so forth. So you could imagine that over the next few years, you will see continued development on number of pieces of equipment, but also on the performance of those pieces of equipment. So watch this space.
There's another one for Sophia there, but maybe if you could just respond to it in writing.
Okay.
Yes.
Well,
we have a few more minutes, so you could also answer live.
Let me just do it in 10 seconds. This is about the tape target system. There's not very many of these tape target systems, so we have to reserve it, and I have to talk to people to do so. So send me an email, and we can talk about reserving it if you do get beam time. Thanks.
Thanks. Daniele, do you have any other, or from the questions that you've already answered?
No, it was very specific and technical. I believe it is satisfactory, the answer, and there was a feedback. So I think we don't need to go again through this question.
Dimitris, do you have any final comments before we close this session?
No, we are waiting for the applications of the audience.
Okay,
right.
Alexandra?
Yes, hi, Sydney. Sydney.
Yeah, I just want to make a short comment about LINP call, okay? The second call. Just
of course.
Just
So
a
Sydney
few-
Gallis is the scientific director at Eli NP, just to introduce you.
Thank you. Just a few additional information. This is a second call. In the first call, we received 15 proposals. Okay? These 15 proposals were evaluated by our PAC, okay? And we have been able to accept and run 100 terawatt experiment and 100 terawatt experiment and 2 1 petawatt experiment, okay? And today, 3 of these experiments were already running. They are done, okay? So our offer in terms of running is a real concrete one. Once it is accepted and validated by the TAC and the PAC, there is a high chance that you can achieve and run your proposal. So we expect for E4 and E5, 100 terawatt and 1 petawatt case, as explained by Sophia, we expect to have many proposals, but we are prepared to accept due to our 10 petawatt commissioning schedule. We are ready to accept 200 terawatt experiment and 2 1 petawatt experiments for the next period, which is going from, as Sophia said, from August to March next year. Okay, this is just want to be a little more complete in the term of what we have done already and what we are prepared to do, of course, and welcoming as many proposals of excellent science possible.
Thanks, Sydney. In that case, let me look around the room, around the screen. If anyone has any last comments before we close this session. I think that's a no. We can't emphasize enough. Please contact the equipment responsibles. Please use our user portal. Please contact us for any questions. The Eli NP deadline is coming up very soon. That's next week, but we have a little bit more time for Eli, the closing of the Eli Eric call. But again, this isn't, we're just ramping up. So the next one, if the timeline is too short this time, then we encourage you to submit it in the next call. So then I would like to thank everyone for participating and say farewell from our side.